All right, so in our last screencast, we basically introduced the Hardy-Weinberg equation and tried to solve some problems with it, ranging from very simple, if we're given P, find Q, to a little bit more complex, finding the frequency of a genotype, to a fairly significantly more complex with a number of individuals. So what I want to do is I want to point out that in this example we did in the last screencast, we were talking about how 90 expressed the recessive phenotype. So now I want to look at a similar question, but this time we're going to say that 90 individuals express the dominant phenotype. How do we do that? Well, let's take a look, shall we? Let's go to the webcam here, the dot cam, and bust that out. So you can see I'm prepared with my calculator this time. So in a population of 1,000 individuals, 90 express the dominant phenotype. So if we say dominant phenotype, the dominant phenotype is actually p squared or 2pq, right? Because that's homozygous dominant, that's heterozygous. Both are going to be the dominant phenotype. So that is going to equal 90 over 1,000. Now, as you learned in math, if you have two variables in one equation, you're in trouble. So this isn't going to work. We need to come up with a different plan. And the plan is actually very simple. Always start with Q. You always want to go for Q first. So I'm going to say, all right, well, Q squared, if P squared plus 2pq is equal to 90 over 1,000, then Q squared must equal 910 over 1,000. In other words, if 90 of the individuals are dominant, the other 910 of those 1,000 must be recessive. So at this point, I again do my square root thing, and I find that Q is equal to, give me a moment, pretty good calculator, huh? Just bought this for my son. He wasn't that interested. He said he just uses computer, but whatever. I like it. So if I do that, I get a Q value of 0.954. So let's say 0.95. And then since P plus Q is equal to 1, that tells me that P is equal to 0.05. Okay? So now, once again, I've got my P and my Q, and I can go ahead and solve whatever problem you throw at me. So how many homozygous recessive individuals are there? Well, homozygous recessive is going to be our little a. That is going to be Q squared. That is going to be 0.95 squared. And 0.95 squared, maybe you see what's about to happen to me and are already laughing at me. That is going to equal, 0.95, 0.9025. And then if we multiply that by the total number of individuals in the area, that's 1,000 individuals. And so that is going to be 903 individuals. Now, what's kind of funny is if I hadn't rounded off my Q that way, I actually would have gotten 910 individuals. So I took a very roundabout way of getting it. So this is the result of rounding. Oh, this is the result of rounding down here. The unrounded, if I hadn't rounded Q off, I actually would have gotten 910 individuals, which is kind of like what it gave me in the question. So I showed you a roundabout way of getting an answer that was already kind of there. But the process will be useful for other problems as well. So that is actually all that I wanted to say about the mathematics of the Hardy-Weinberg equation. So just like any time you're dealing with math, practice is important. And you know, you're gonna there's some in the homework packet, we're gonna have a lab with some problems, so you're just gonna have to do some practice. And again, remember, always start by finding the frequency of the recessive genotype, use it to solve for Q, and then the problem kind of unfolds from there. So with that, on our next screencast, we are going to get away from the math and look at more of the conceptual aspects of the Hardy-Weinberg equation. So look forward to that, good children.